All right. Welcome, everyone. Let's get started. This is our November meetup, Generative AI on AWS. Thanks, everyone, for joining. As always, we do have a packed agenda today with exciting speakers. So super happy to welcome Joe Reis. Joe is going to present the new data engineering course available on DeepLearning.ai that he built. So that is a very comprehensive course. So Joe will walk us through the highlights today. And then we also have Shivam and Apurva with us today. They gonna talk about how to serve LLMs with Amazon EKS. So if we have Kubernetes fans in here, and Reis. And as you probably heard, last week was KubeCon. We've been chatting around here. And Chris also was attending KubeCon in Salt Lake City. And Chris, what do you have? You have a summary about GPU highlights, right?
Yeah, there were more GPU highlights in this one KubeCon than there has in all previous KubeCons, and GPUs with Kubernetes. So I've got about 20 slides. I'm just going to highlight some cool things. So stick around for that.
All right. So with that, I think we have a full agenda. Just quick housekeeping notes. We are recording this meetup. So in case we're running over, everything is recorded and will be posted to our YouTube channel. We'll put the link here in the chat in a second. And you have the chat. So if you have any questions for the speakers, then please put them in the chat window and we'll make time briefly after each slot to go over the Q&A. And with that, anything else to add, Chris?
No, I think we should hit it.
All right, Joe, take it away.
Will do. Hey, everybody. I'm Joe. It's good to see everybody here, see some familiar faces in the comments here. So feel free to heckle me as I talk. It should be fun. So anyway, at the risk of turning this into an infomercial, I kind of want to walk through the motivations behind making a book and then a course, right? So um, the motivations behind writing a book on data engineering were, I think, my co-author Matt Housley and I were kind of, running a data engineering consultancy, which we've run for a long time, Ternary Data. And, this is during COVID. I think everyone had a COVID project. I started gardening or baking bread or finding some hobby. We decided to consolidate the knowledge of data engineering. We felt like when you looked up what is data engineering on the internet, you typically come back with, I'd say, some pretty iffy responses, right? Some people would say that data engineering is Hadoop and Pig and Hive and, attaching it to technologies really, right? And in other cases, I would see some advice about how to get into data engineering, and it would be about, well, you should learn dimensional modeling, right? So Ralph Kimball's book would always be thrown out there as one of the go-tos and so forth. And really, it felt like this was nobody had really taken a deep dive and to really understand, okay, and describe what is data engineering, from a set of first principles. And so, we had gone ahead and we talked to some publishing companies. We talked with uh, O'Reilly, who I'm sure all of you know. And the initial feedback was, you actually shouldn't do this book. So they tried to dissuade us from doing it. That mainly because it's like, why would two first-time authors try and define a field from the ground up, right, in a technology agnostic way? So it was gonna be a very hard book to do, but we decided to do it. We finally, got the go ahead and wrote the book. It took us around a year and a half, and really, the fundamentals of data engineering. The focus on this is really a technology agnostic, first principles view of data engineering as a field, right? So we cover things like, the data engineering lifecycle, which really encompasses everything from, getting data from source systems, ingesting it, storing it, transforming it, and then finally serving it to downstream users like analysts and data scientists. But along the way, right, there's undercurrents, things like security, data management, orchestration, software engineering, and so forth. And this is great. This book took off, and as far as I know, it is the staple of data engineering uh, curriculum around the world now. It's used in, I think, given lunch and learns at, I think, every major tech company, every lots of universities, lots of user groups worldwide. And so it's really cool to see. We didn't expect that kind of success, but it's about 2 years into the book being published. And, I think by all accounts, it's, a lot of companies are using it. Even the US government's using it. I remember getting a call one day from somebody from one of the branches of the military saying they're using it. And so it's cool to see. So, what's spawning from that is a lot of, courses, degree programs, college specializations and so forth, focus on data engineering. So it's really cool to see, right? And the fact that the book was the cornerstone of that was, I think, really, really humbling, and it still is to this day. But the thing that I always thought that was missing from the book was because we didn't focus on technology. The thing that was missing is where are the hands-on labs? We can get questions about, what technologies would you recommend a data engineer use today? And, I mean, for the longest time, I tried dodging this question. I was like, well, I don't know. You should pick what makes you happy, right? Or something like that. But that's kind of a non-answer, really. I mean, at the end of the day, people want to learn data engineering using hands-on examples, preferably using cloud technologies, right? So I'd say around, what was it? Winter of 2023, I get a message from DeepLearning.ai. And at first I thought this was a joke because I was like, why would, Andrew Ng, why would it be on his radar, in Deep Learning's radar? This seems a bit interesting. But then it made sense. Andrew Ng's been pushing data-centric AI for quite some time, I think since 2021. And the notion behind data-centric AI is, data is really the core component of successful AI. Without good data, good useful data, it really doesn't matter what type of hardware you have. It really doesn't matter the type of algorithms you throw at it. It really is a garbage in, garbage out problem, or a data in, data out problem. And so Andrew took I think a very hard focus at data engineering and realized that this was one of the missing pieces. More broadly in the education space, from a course perspective, but also from an offering from Deep Learning AI itself, right? So we started working on what do we think a course is going to look like. And this ended up being a monstrosity. I think it, I know Chris and Antje, it took like, I think you guys worked several months on your course, and it's a great course. I've taken at least half of it, and so I think you understand how hard it is to make a course. This course took over a year to build, I think, and some change, right? So, but I think the end result is something that is something that I'm proud of. Like, I think I had every company wanted to, before Deep Learning reached out, I had pretty much every single company wanted to go do a course based on fundamentals of data engineering, and I turned them all down. Right, I didn't feel like, for one reason or another, I didn't feel like the quality was going to be there in terms of really representing what I felt should be a good home for the book's material. Right, I really wanted something to stand the test of time. And so, having taken Andrew's courses in the past, I knew that, he's very focused on just the highest quality possible. There's nothing that really slips through this, what Andrew's trying to convey in his education. And so I really took that seriously when deciding to partner with Deep Learning. And shortly thereafter, we decided to partner with AWS, right? So it's a course that has the hyper focus on detail and quality that Deep Learning AI provides, as well as the rigor and and showcases AWS in the finest possible way. We worked with, I think, the cream of the crop from AWS to make this work. And the result is this course, right? So now we have on Coursera data engineering, right? So this is really cool to see. I think there had been some prior data engineering classes, but again, they're very focused on, I think, I don't know, the curriculum. I noticed other data engineering courses, it was all over the place, right? Like you were focusing on, it was almost too much tool focus, where I really want to highlight that the data engineering lifecycle and the undercurrents come first and the tools come second, right? So what does this mean, right? If we focus on what this course provides, we're looking at a 4-course series, intermediate level, right? And 3 months of work. You can do this at your own pace, but I would suggest staying with it. The really cool thing is it highlights I think a lot of the practices that I think that data engineers need to know today. And what would those be exactly, right? In a lot of cases, we're talking about things like, if we go to this course here, the first one, the first two courses actually, for the first 2 weeks open up with, describing what data engineering is from first principles, but really also being able to focus on things like architecture at a high level, as well as translating requirements. So this means talking to stakeholders and business people, something that I don't think any course really does. But if you ignore this, then you're just building a bunch of tools. But if they don't satisfy a business outcome, I think you're doing a real disservice to the company you work for, and also your growth as a data engineer. So we really wanted to highlight early on how to think like a data engineer, not just how to use whatever technologies happen to be the flavor of the day. And a lot of people, I think this is a big gamble, but a lot of people like this part of the course, right, where it's very focused on the thinking aspect, and it really sets a tone for the rest of the course. So in this case, you're hired as the mock scenario is you're hired as a data engineer at an e-commerce company. Could be any e-commerce company. Um, but you're tasked with revamping a lot of stuff to provide better analytics and also machine learning modules, right? And generative AI for a bunch of use cases. So a lot of this first part of the course is just understanding, okay, so like, what am I trying to build? What am I trying to do? And instead of the tendency for engineers is to jump straight in, build a bunch of stuff that nobody even asked for, right? So this is, I think, to save a lot of people from themselves, this part of the course here. And then you start getting into some interesting things, right? So you get into, let me see here. Where is that other part of the course? So then we start getting to the life cycle part, right? So if we talk about, yeah, so again, this is first part of the course here. But if we go back to, sorry, I'm clicking on wasting time here. But if we go back to the course here and look at some other parts of it, right? I think, again, this is the kind of course I always wanted to build, where now we're talking about source systems, data ingestion, pipelines, and so forth, right? This is course 2, 34 hours of material, by the way. So lots of hands-on labs. So in this case, we're getting kind of into the deep diving into really how do you work with AWS, right? So we had Morgan Willis from AWS spearhead a lot of the content here. She's, if you don't know, one of the I think one of the more highlighted trainers on Coursera with AWS, and so she was an asset to this course for sure. And then basically, you go through lots of labs. So the whole idea was to provide a course that, where this book really we intentionally ignored technologies. Because we want to have the book have longevity. In this case, we're trying to provide a lot of hands-on examples, really highlighting how do you build data engineering systems? How do you think like a data engineer and operate like one? And so all these courses really dive into it. You get into from source systems, you get into data storage and queries and so forth. And like this goes into kind of the nitty-gritty of hot warm storage data, for example. And again, labs galore, hands-on stuff galore. We also had Navneet Shukla from AWS also did a few labs on, I think, Airflow. But really, this is a very comprehensive course. And the other cool things is going into things like modeling, right? And data warehousing and so forth. You have Inman versus Kimball. A lot of discussions like this. The other cool thing is we, going through, we have other technologies at DBT. The cool thing I want to highlight too is we had conversations with a lot of the people who were instrumental, not just for this course, but also in the field of data. So Drew Bannon, for example, wrote the first lines of DBT. He talks about DBT, right? And I think this course here we have people like Sol Rashidi, who's now at Amazon. We have Jordan Morrow, the godfather of data literacy. Bill Inman, who designed the data warehouse. He features very prominently in this course. And so, this is, I would say it's as much of a way to, learn the techniques of data engineering, as well as get, I'd say some quote face time with, some of the, people who I consider to be the leaders in the field. You know, we had Wes McKinney from who designed created pandas and Apache Arrow. He's in the course. So I think it's I kind of wanted the course to be almost an episode of Curb Your Enthusiasm where there's lots of cameo appearances by a lot of people who you know, I consider to be, you know, very influential you know, kind of celebrities in the field of data. And so in a nutshell, this course is, right. I think it's sort of, like I said, the yin to the yang of the book. Hopefully this course serves you know, a broad audience. If you're a software engineer, data scientist, a data analyst, or somebody interested in data engineering, I would recommend taking this course. It's, you know, inexpensive, and you know, hopefully it adds a lot of value. So anyway, that's the course. Thanks to AWS, you know, for the great support on this. I think by all accounts, this is one of the most popular courses on Coursera right now. So so yeah, anyway, I can leave it open to a couple questions. Otherwise, you know, happy to pass the time over to the next presentation. So, and thanks for your help on the course, by the way, Chris. I know you were also involved in some of it. So yeah, thank you.
Yeah. Yeah. How did all that turn out? I know those labs got pretty complicated, and I guess I love a question. How many services from like AWS to the labs end to end? Probably like 50, right? Something.
Oh, at least, yeah, at least. I think by all accounts, this was the most complicated course deep learning's ever made by a long
Yeah.
shot. Because I think they're like, oh, it should just be easy. We'll just use notebooks. And it's like, no, I don't think you understand. You're going to be using like most components from AWS. And so, yeah, the labs were a lot of stuff. So.
Have you had to debug like issues with the labs and things? I know we spent almost a year like debugging thing. We're still debugging things in
Oh
those
yes.
labs. Yeah.
Yeah,
That's
they know that everyone's still ongoing. So how much does it cost? I mean, some course, some audience questions. How much it costs to take the course? Whatever it costs to take a Coursera class is how much it takes, assuming you want the certification. So it's not available through Coursera Plus. You do have to pay for it outside of that, but I would say it's well worth the time when you consider what, $150 for an investment in learning data engineering. I think it's a pretty good deal, given what you get.
I think you can take it for free
You can audit it. Yep.
but you don't get the labs and you don't get the certification.
Correct. Yep. That's exactly it. Yeah. We have a
That was really
question
hard to.
for some. Yeah, it is. Yeah, without the labs, I would say you're missing out on, you just watch a bunch of videos, but I'd say do the labs. That's where you're going to get the benefit, right? So,
And the labs are included, right? So there is no extra cost for running the labs.
Correct. Yeah. So the benefit of that is if you were to try and do this on your own, I would say have fun with that. Um, you'll be spinning all this stuff up on your own AWS account, and I don't even know how you would do that. But anyway, yeah, take the course. We did a lot of the hard work for you. So
maybe quick, yeah, on the
go ahead, Antje.
prerequisites, right? I know data engineering can be a lot, as you said, like, so what is the prerequisites for people to take the course, like the bare minimum?
I believe it was Python and maybe some SQL, but more just a willingness to learn, I would say. You know, it definitely helps if you're coming into it from a data adjacent field or software engineering. But I think more than anything, just given the comprehensive and long nature of the course, it's 16 weeks of material. Like I would say, just like be in it to win it. But yeah. But the completion rates are pretty high from what I'm seeing. It's higher than normal. I think people are really sticking through it. So it's cool to see. But yeah, 16 weeks is a long time for anything. So I got some questions here. How does DJing influence my perspective on data? It's no comment. How could you advise learners on how to get into AI data position? You know, I think with anything, doing a course is great. Getting a certification is great. I actually wrote about this over the weekend, where I think the really important thing you need to do is build your network of people at the companies you're interested in working at, and really get to know, you know, kind of what types of companies you want to work at, and really focus on those, and maybe making some friends there. And also just learn AI. I would say take the generative AI course, you know, from Chris and Antje as well. That's a great course, and then just continuously learn. I mean, this field is changing so quick that I don't even. I mean, I've been doing machine learning for ages, and I feel like Rip Van Winkle some days. I just wake up and I'm like, I don't even recognize the world I'm in. So it's just, you just got to, I think continuously learning is how you get ahead and how you get the career eventually, but also knowing who to get the career from. But yeah, it ain't easy, but you know, it's I don't know. What do you think about that? I mean, getting a career in AI these days. You have any thoughts?
Yeah, I mean, understanding the fundamentals obviously is important. Yeah, like I mean, there's this AI engineer sort of persona role now that where you don't really, I guess, need to understand the fundamentals. You just actually, I heard a really good podcast this weekend. I think it was the Lex Friedman podcast where it was a 5 hour podcast with the Anthropic folks,
Hmm.
and they talked to the person who actually writes the system prompt for Claude.ai, and she describes like how she like iterates and thinks about there's a philosophical area to how you write prompts, and you have to
Hmm.
think of the model as a human and how you would speak to a human, and you want to provide clarity and stuff. So yeah,
Interesting. Yeah.
um, not many people are really training their own foundation models these days. There's, the top models, and then it's just kind of finding
Yeah.
good use cases to build.
I
Hmm.
think it opens the door for many more to join the space, right? Because there's obviously people, that go deep and in the science part and build models and train models. But there's also this complete new generation of people that, join the space and are using AI to build really cool things and the next generation of applications, right? So it's kind of broadening, which I'm excited about the space to many more to, not everyone needs to build a model,
Yeah.
but you can just, learn how to use them effectively, learn about the prompt engineering, learn about ways to customize it for your use case, and then build amazing applications. So I
Absolutely.
think, it's a broad space these days, which is to me super exciting. So I think people can pick the area they're passionate about, and then just like constant learning. I think this is just way more than the tech space has seen before, right? Like innovation happening at a speed that's just amazing.
It's insane.
Yeah.
Cool. Final question. Would you ever do one of these deep learning courses again?
Yeah, I absolutely would actually. I felt like it was one of
Yeah,
the best experiences I've ever had. I don't know about how you felt, but I felt like the attention to detail was so
yeah,
uh on top of things. Like I would get Slack messages asking me, "Can you just re-record this word?" And be
yeah,
like, "Yeah,
yeah,
okay." It's
totally.
wild. Yeah. Do you feel the same
And
way?
like, would you have to fly back into Palo Alto to do it, or did
Probably,
you?
yeah, for the
Yeah.
institute, but that studio is like a second home at this point, so it's fine. Spent so
Oh
much time
yeah,
there.
yeah. You had all of your like guest speakers had to fly out too, right? Had
Yeah,
to be
quite
in
a few of
Palo
them.
Alto and
Yep.
stuff, right?
So, yeah.
Yeah, I think I would probably need a little bit more time in between because that was our second one. And
Mm,
so, I mean, same with the book too, right? We we have a book that goes with each of
yep.
our courses as well. And I think I'm going to take a break from the book. Yeah, I really liked working with the O'Reilly folks. They pushed back quite a lot on us, and really, because at first we were not going to do multimodal, and then they said
Mm,
no, you have to do multimodal, and yeah, ultimately that was a good decision. We were worried about the book being just way too massive, and we are able to
mm,
scope it down to 300 pages. But yeah, how long is like your book?
interesting. 450.
Yeah, yeah, our
Yeah, and
first
I
one
think we had
was
700
499.
pages written, but we had to
Totally,
cut
we
it.
did too.
Yeah.
We
Well,
did
that
too.
it's impressive to bring it from whatever you had to 300 because I mean that's
Yeah,
really like, essentialism at that point. Like
yeah.
what do you really need? It's hard. So for the
Totally.
audience out there, if you ever want to write a book, just know writing is the easy part, editing is actually the hard part, I think.
Yep. The
But yeah.
figures and matching up. Yeah. Doing the figure log was always like exhausting.
Such a chore.
But okay, cool. We do
Yeah.
have to
Thank you.
move on.
Of course.
Thank you, Joe. Always
Thank you.
great to see you.
Yeah, likewise.
And
Yeah.
Thank you.
Shivam, you're up.
All right. Let me start sharing my screen. Share. Okay, can you see it?
Not
Not
yet.
yet.
Okay. Okay. I think should be up now.
Yeah.
Yeah.
Awesome.
Excellent.
Awesome. Hey everyone. Nice to meet you all. I'm Shivam Dubey, Associate Specialist, Solutions Architect, focusing on containers, based out of Dallas, and I help customers to get most out of AWS. And with me, I have my awesome colleague Apurva. So you can like ask any questions in the chat, and he can answer that. All right. So here we're gonna talk about like how do we scale LLMs, right? Specifically with inferencing. So think of it like this is a sample chatbot. You can think of that we are using, and I'm giving a prompt here like, what is NQPU? Just nothing but a random prompt. And I sent the request and I got the request, hey, NQPU stands for noisy quantum phase uncertainty, which I'm not aware of. Then what I'm doing is, right, I'm uploading my sample.txt, which is the technique called RAG. And then what I'm doing is like here, the NQPU stands for something else, Neuron Quantum Processing Unit. So what I'm gonna do now, I uploaded my sample.txt here, and now I'm gonna ask my model the same prompt. Done, send. Now we're gonna see that what we are getting. So here, Neural Quantum Processing Unit, quantum entanglement, and a lot of things, right? And now when we uploaded the .txt file, now we are getting the response from the txt file. So model is now reaching out to the txt files, RAG is happening, and that's how you're getting the model. There are a lot of use cases that we are seeing it from the customers, basic chatbot, RAG, fine-tune, and then serve the model. But this looks, from the user's perspective, it looks much simpler, because our job is like, if I'm a user, I am just giving my sample prompts here and I'm getting the result, right? But think of it like where the model is running and how does it behaves when like thousands of users gave the prompt at the same time. So how does those scalabilities and everything happens? Is that what the biggest challenge when we talk about LLMs? So continuing towards the challenges. So these are the few challenges. The first one is definitely the concurrent execution, as I was talking about, because giving single request is fine, but when you have teams or everyone, when you are like, think of it like if you are hosting model on yourself, how do you manage those scaling? That's important thing. Right now, we also seen a pattern that one model doesn't fit for all the use cases. Like some model is good in summarization, some model is good in coding, for example. So multi-model serving is also example on like how with a single pane of glass you are serving the multi-model, because you don't want to host everything like separately, and that's what our biggest challenge is. Next is batching. You want to batch every request just to save some cost over there. Latency is also important, right? Like latency is critical, especially when some model takes 10 to 15 seconds response. So those times also, like how you are tuning, those things are also important when we talk about the challenges. And the flexibility as well. You might be heard of TensorFlow, PyTorch, those frameworks and backends, VLLMs, TensorRT. So how do you want to use all of these things together, talking about multiple protocol like gRPC, HTTP, everything, like when we see like on this scaling perspective, running all of these things together is a big challenge. So we're going to talk about next how this thing can be solved. So for that, we are going to talk about Ray, which is an open source unified framework for scaling AI and Python applications like machine learning. It is easy to use as it provides the compute layer for parallel processing so that you don't need to be a distributed system expert. And here, this libraries covers like end-to-end model life cycles, like from pre-processing to serving, thereby shortening the time of production. So this is what like if you can see, you are gonna see in the demo like how we are serving the model. So those scalabilities and everything will be taken care by the Ray, and we're gonna see in the demo. But yeah, this is just for the people who don't know what it is, just an overview. And another thing, the backend is here VLLM, which is a high throughput and memory efficient inference and serving engine for large language model, especially designed to optimize deployment and inference performance. So a standout feature is the page attention, which you can think of as a paging. So what does it do? What it does is like so we try to optimize the GRAM when we run our models in the GPU, right? And there VLLM can help us. And another key advantage of VLLMs is efficient memory sharing during parallel sampling, where multiple output sequences are generated from a single prompt. This reduces memory usage by 55% and improves throughput by up to 2.2 times. So these numbers are increasing and increasing. You're getting like really good low latencies and everything when they are publishing the new versions. So everything gonna be like getting efficient as we are passing the time now. So these things I was talking about Ray, and there's nothing. All of these things like if we ignore it for now. So when we talk about Kubernetes, there are two important concepts when we create the resources. So first one is controller, and the second one is operator. So the controller will be like, think of it like a application load balancer controller that will create the load balancer for you, the AWS resources, right? And then there's an operator. What it will do is like that will create the resources of the Kubernetes, right? Suppose if there's an operator, right? Like here gonna talk about the kubery operator. So let's talk about it. So to like have a clear understanding. So now you know about controller, let's talk about operator. So imagine you are using Ray for scaling Python application, especially in AI and ML space. So Ray, we already know, which helps you distribute tasks across multi-machines, which is great, but there's a difficulty in the cache, and managing those distributed system can be difficult. That's why KubeRay comes in. KubeRay helps in deploying and managing Ray cluster in easier way. It leverages the powerful orchestration capabilities of Kubernetes, but tailors them to fit the unique needs of Ray. So instead of manually handling all the details of scaling, resource allocation, and fault tolerance, KubeRay take cares for you. So this arrows are here not so important if you are familiar with the Kubernetes operators. It's just the standard patterns of the operators. The summary is that both Ray and Kubernetes serve as the resource orchestrator, but they focus on different aspects. Ray is all about computation, handling tasks and actors, while Kubernetes is geared towards the deployment and managing its scheduling units. So this is like an abstraction between the data scientist, the ML scientist, and the infrastructure engineer, so that the infrastructure engineers can take care of the Kubernetes, and then the data scientists can take care of their just Ray cluster with this Kubernetes operator, with the kubery operator. So now we know that like, yeah, ultimately the operator is gonna create the Kubernetes resources for you. Diving a bit deeper now. So this is how we are solving the scaling challenges with this part of the demo. And this is the architecture of what we are doing. So here you can see the architecture. So this is how it's gonna work. You can see here. So first, let's talk about Ray. So when we deploy Ray cluster, there are two concepts, right? The head and the worker. Head is where the processes is gonna run, and ultimately the pod, the model is gonna be taken care by the worker node. So you have the traffic here. User sends the request. It goes to the network load balancer, and then this Ray exposes service. And then after that, you can see here the head node is running on the CPU because it's just like you can think of as a controller, but the worker is where the actual model is running, and that's why for that we need GPU. If we go a next step here, you can see FSX cluster, which is nothing but a file storage, AWS file storage. And when we work with LLMs, the one of the important point to consider is the size of the image. These models, like if you talk about like Mistral 7B, the model weights are so heavy. And when we use like Reis, VLLM and other libraries that you use, then image, when you create the image, that is becoming like that will become heavier and heavier. So how to make it much faster when we scale? Because like when the scaling is happening, you don't want for the pod to wait for 10 minutes to pull the model from the registry and then start the process. And that's why right now what we did is like we have loaded the model into the FSX cluster so that these of the things will be connected to the nodes, and we have PVC so that like whenever the scaling is happening, we will be avoiding the cold start and the scaling will be happening in the right way. We have Carpenter also, which is our node autoscaler, so that when when the scaling is happening, when this node is out of resources, then what Carpenter will do? Carpenter gonna create a new node for us so that the pending pod gonna be scheduled on that new node and the traffic gonna serve. Prometheus, Grafana, we know like if you want like customized metrics, you can definitely use a much deeper picture. So again, as a user perspective, we don't care, right? Like we are just giving the prompts and getting the results, but thing looks much different, right? When we see that how the traffic is flowing from ports and everywhere and how does it goes. So typically so this is the request flow of like how when we query, when we give the query, when we give the prompt to the model, like how does it goes behind the scene and we get a result within a second or maybe 2 seconds, but there are a lot of things that goes behind the scene. So typically the process starts when a client tab sends a query through Reserve API here. And this can happen through either like gRPC or HTTP, depending on what's being used. Once the API layer receives the request, it moves towards the dynamic batching mechanism. And this part is interesting because it decides like how to batch the incoming request based on the model you have chosen. Internally, it uses multiple queues to handle and scale the batching process, ensuring efficient processing. And then we already talked about this FSX, right? Why we are using FSX. So people can use like Hugging Face as well, but that's gonna lead to cold start because pulling the model from Hugging Face is gonna be a single threaded process. So it takes a lot of time to pull the model and then load the model into the memory and then serve the traffic. So again, tying up with this, like this is the reason, like to avoid the cold start, we are using FSX for Luster here. Then after queuing and everything, the request goes to the VLLM backend, and that's how you will get the prompt, this result back. So there are a lot of things that goes when we give the prompt and get the result. And one more thing is this setup is hardware agnostic, whether you can use GPU or you can use AWS neuron chips like Inferentia to run this thing, to run this pattern. So we already talked about Carpenter, right? And how the Ray cluster works with the concept of head and worker. So you can see here, right, that the head was running in CPU node. and the worker were there in the GPU. So important thing to consider is like as the carpenter provides you the flexibility of using the spot instances as well, but all the time we want the head node to work on on-demand instances, because like that is the main controller that we don't need any interruption, and that's the reason we run the head pod in the on-demand instances in that node. But the worker pod can run on spot instances, and those flexibilities you can get it with the carpenter. And if you want like further optimizations on the towards the cost saving, and you want like better price to performance ratio, you can use Graviton, and we have like a AWS chips as well, like Trainium, Inferentia, that you can use as well on behalf of the GPUs. All right, a lot of theoretical stuff that we talked about, but time to see the demo. And we are gonna talk about like all the architectures, Ray, how does it looks like, Prometheus, Grafana, everything here. So this is my Kubernetes cluster, and I have already deployed my Ray manifest. So that's the reason you can see here there are tubes. So when I run the so these parts in the Racer VLLM Race a namespace, and when I run this thing, you can see here like we have two parts. The first one is the head, and another one is worker. So Carpenter works with the concept of node pool, where you specify like what are the resources you want from resources you want from the AWS, right? For example, how can I specify that this head should work on CPU only? I don't want head to run on GPU, and I want this worker to run only on the GPU. So there's a concept of node pool where we specify all those details. So we have two node pools, the GPU and CPU. The CPU is for the head pod, and the GPU is for the worker. So these are the node pools we have, and this is how this is gonna looking like. So the worker is running on spot, and the head is running on demand, which is m5.x large. And again, head CPU, worker GPU. Next thing we are gonna see here is the Kube Prometheus stack. So with this Terraform stack, we have a Kube Prometheus stack along with it, so that like we're gonna use to see that how does it perform. This is Ray dashboard, which will give you. So we were talking about the Kube Ray operator, right? And when we are using Ray service, the Ray, you will get a good dashboard with it. And with this, like this helps like really to debug like what is happening, if something went wrong. All of these things you can check here in the serve. One replica, we see that you can see like actors, logs, everything you can see of your Ray cluster, how does it performing here in this Ray dashboard. Next is like we are using Prometheus here for the metric collection, and you can see here we have Ray worker and Ray head as well. So next we are using Grafana to like see like higher visibility of like how our GPU RAM is getting consumed, how the tasks are getting a response and everything. So this is our client.py. Okay, let me go back here. But yeah, this client.py, what it will do is like it will just like we will be giving API here, our Racer API, and this is gonna generate the prompt. So that's what I'm running client.py, where we are using Racer VLLM endpoint. So I'm gonna running client.py, which is ultimately like we have prompt.txt. Okay, yeah. So this is prompt.txt, where we are running we are getting the results of this prompt, and that's what the client.txt is looking at this prompts and will be generating the results for us. And the results are getting generated. That's fine, right? And you can see result.txt, and we have results of all the prompts. But this is not our goal. So this is the single request that we are giving, and you can see the spikes it here. So as in the beginning, we see that I talked about it, right? Like running giving simple query to prompt is definitely, it can take care of it, right? But how does it behave when thousands of users request the model? How is those scaling happening? That is what the challenge we are solving. And for it, we have seen that like we're giving the sample prompt, like 4 prompts at the same time. We are getting the response, no scaling, nothing happened. We just get the response for what we requested. But now, taking a step ahead, we are gonna do some load testing and gonna see that how our model behaves. So we have a script called like load test.py. What ultimately it will do, it will generate a few concurrent requests to the model, and we're gonna see that like how model behaves when we talk about the concurrency, and running this load.test.py multiple times, so that like just to make it much faster. And you see that like load testing is done, replica is one. So gonna check the pods again, kubectl get pods. You're gonna see the behavior now. So checking the pods again. So right now you see that there are still 1 replicas and the load is still getting generated. So first, what is happening now? So the load is going towards the existing pods and the existing nodes, and the scaling will only happens like when this node is out of resources. So our script is still running, and when we are running kubectl get pods again, now you see that the scaling is happening. We have newer nodes as well. And you can see here the maximum replicas is 3. Before that, it was just 1. So that is how the problem we are solving, like how fast scaling that you are getting. Spikes also, you can see here the number of tasks, it got just shoot up because of our client.py. Gonna checking it again, gonna see the bar. So you can see that like these two, we have 2 of the nodes right now, 2 worker, and other is in the init state, which means that the node is getting created and the processes, the model is getting pulled on that. So this is how fast it is, right? And this is how the scaling works when we talk about LLMs. And in this here also, you can see here in this EKS node viewer, you have now like 1, 2, 3 worker nodes here, and this one is getting created. That's why like it is getting processed. So our this setup, the Racer and VLLM was able to serve the traffic, and the maximum replicas here, it reached to 3, and you can see still that the load is being generated. So another important factor is just not the scaling, right? Like what if my traffic got served, what will happen to the nodes, right? Like I don't want, like if there's a node traffic, that I don't want my nodes to be just idle. I want them to be terminated. And that's what the flexibility with the Carpenter that you get, that when there's no traffic, you can set the parameters like how long you want to keep the node active when there's no traffic or something. And that's what you can get the advantage and the optimization over there. So if there's a no traffic, scale, serve the traffic, no traffic, wait for this time, terminate. So that's how you can save the cost over as well with the Carpenter. So this whole setup is work on the cost optimization, and you can get like a good results with this. So we talked about this, and the important thing to talk about here, one last thing is here is the maximum replicas. So those things also you can specify that whenever the scaling is happening, like how much scaling that you want. So here I have gave just the hard limit of 3, and that's why even the load was getting generated, the replicas were 3. And you can give a hard limit here, like what's the minimum replicas and what's the maximum replicas to have, so that you can have those control over it. All of these things that we talked about, Reis, VLLMs, GPUs, neuron, everything, we have it in our data on EKS blueprint. So data on EKS is our AWS project where we build patterns on behalf of customers. And this is an open source project. So if you are interested, definitely you can contribute. And if you are, if you think that any of the emerging patterns, or if you are using any of the use cases, you can create a GitHub issue and we can start working on it. All of this, like best practices, different GNI patterns from inferencing to training, everything you can be found here. And the way, I mean, the thing Racer and VLLM is also here, and all the things are really in good instructions that you can just follow step by step, and you can deploy at your environment. Last thing before closure. So we do have our GenAI workshop, and also as reInvent is coming up, so which is in like December 1st week, 2 to 5 December, I believe. So we are reInvent is nothing but AWS conference where we are gonna talk about our new launches and like a lot of workshops and deep dives that we are doing. So we have a lot of workshops, chalk talks that we are doing. So if you are going to reInvent, please attend these sessions. And if you have anything regarding to the GenAI, do hit us up. All right, with that, I am open to taking some questions if you have any.
I think Apoorva's answered pretty much all of them.
Awesome.
Yeah, he was doing a good job there. So I guess, how many talks are there on EKS? Wow, there's a lot here.
Oh yeah. So it's like all from everywhere, like from cost
Yeah.
optimization to resiliency to IDP. We are everywhere.
Yeah, and it looks like there's 10, 11 talks just on like ML and Gen
Right.
AI.
Yes.
Sweet. ML ops, stock talks, and breakouts and stuff. Okay,
Yeah.
cool.
There's a question, can reInvent sessions be attended virtually? So the breakouts and some of the chalk talks, they are recorded, and so they can be viewed on YouTube later. The keynotes, you can live stream them as they happen. These will happen on each of the reInvent Day morning times in Pacific time zone. But yeah, the breakouts and the chalk talks can be viewed later on YouTube or something. Right, Antje, I think you're the expert on how to obtain these, but I think
Yeah.
I've covered those.
Yeah,
For
no,
the
that's right.
workshops and the hands-on labs, unfortunately, those are not recorded for reInvent. If you wish to run those in your teams, in your AWS accounts, I've sent the data on EKS GitHub link. Those can be run in your accounts in a DIY fashion. But if you need help running them with a instructor-led session, please reach out to your account essays, and they can circle back with us, and we can set those up for your teams. We have some labs that can be run internally within your organizations.
Sweet. Okay, I think we've got about 6 minutes, so I'm going to try to get through 25 slides in 6 minutes. Thank you, Shivam. Thank you, Apoorva. Yeah, always great to see you too.
Thank you.
And
Thank you.
okay, let me try to get as far as I can here. I'll probably go over by maybe 5 or so minutes. I'll keep recording, and if you do have to drop at the top of the hour, you can watch the recording. I'll post it later today. So let me share my screen, get the Zoom action out of the way. And oh, now I lost Zoom. Where did Zoom go? Share my screen. Going to try to put my face somewhere here at the bottom, maybe bottom right. Okay. And I'm going to share. Antje, can you see me okay
Yes, we can see it.
with my smiling face? Okay. And I've asked Antje to copy and paste the links as I get to them here, so you should have all the links. The main topic here is so I just got back from KubeCon 2024 in Salt Lake City. I wasn't prepared for the cold because I live in California, and I thought I would never see snow again. And the day that I flew in on, I think it was November 12th, there was a big snowstorm. Well, yeah, not a snowstorm, it was more of a dusting. So I am subsequently sick. I do want to mention that they did announce the next 2 cities for the North America. It's going to be Atlanta next November, and it's going to be LA the following year in October. So I didn't realize that they actually pre-announced these for the next couple of years. I thought they always kind of did it last minute. But so we've got some clarity there, so you can make your travel arrangements. And these are both warm weather cities, so that's good news. So first, I'm going to start by sort of analyzing just the pure number of talks at this single KubeCon relative to previous KubeCons. I'm then going to talk about some GPU sharing strategies and best practices for multi-tenant GPU-based Kubernetes environments. There were a whole number of talks on this. There's been a lot of stuff coming out of the Nvidia folks. They've been working very closely with the Kubernetes community, and I want to highlight some of that work. Also, quite a bit of talk about fault tolerance. This was actually prompted by a very interesting paper that came out of Meta that I'll link to here in a bit, where Meta highlights the number of errors that they had with GPUs, physical hardware errors, and errors at many different parts of the hardware stack for these large-scale GPU training clusters. Okay, and I've got links to the full PDFs here. These are from the full talks that my brief summary here, 10-minute summary, is going to cover. So first of all, let's analyze the number of GPU talks versus previous KubeCon. So here we go. So this is the North America, Salt Lake City. There were over 20 sessions just by Nvidia on GPUs. Now, some of these talks also had people from Intel, people from Google, were all there in full force. But if you just search Nvidia, you'll find 20. I think there were 21, 22 sessions throughout this entire event. That's compared to all the previous KubeCons to date, where there were only 13 across, I don't know, was this 5 years? And I don't even think there were any GPU talks, back in 2018. I've been going to KubeCon since 2015, since the very beginning, and it was always hard to just find AI talks, let alone GPU. And so a lot of progress has been made. And yeah, as you can see, this isn't just NVIDIA. This is also IBM. This is Google, and like Intel as well. So a guy to pay attention to if you're looking to find someone to stalk online is this Kevin Kleus. He actually lives in Berlin, and I first sort of started paying attention to him from some of the blog posts that were coming out on the NVIDIA blog site. And he's right in this mix of trying to get GPUs to work with Kubernetes. So he had about 5 talks at KubeCon. Okay, let's talk real quick about some strategies for multi-tenant GPU. So why do we want to share GPUs? Yeah, obviously we want to try in a multi-tenant environment where we have lots of different users trying to share our GPUs, or we have lots of different researchers trying to share a GPU cluster, large 10,000, 100,000 GPU cluster. It's nice to be able to share some of these resources when you're using Kubernetes. Up till I think a year or two, there really was there was no way to actually share. You certainly couldn't fractionalize the GPU even just a couple of years ago. So we've made a lot of strides, I think. And also pay attention to this DRA. So this came up in almost every GPU talk with like Kubernetes. So dynamic resource allocation, DRA. This is a Kubernetes driver that helps you to share these resources and to actually slice up the GPU and share them amongst multiple tenants. Okay. The very first DRA adapter or driver came out, I believe, in Kubernetes 1.2.6 as alpha, and it's taken 6 releases to actually go to beta. And now that it's beta, more and more of these Kubernetes providers can start to now offer this functionality. So before it was kind of one-off solutions to do this stuff. So it's really in its sort of V2 form. They're actually deprecating the what they're calling classic or V1 version of dynamic resource allocation driver. And if you're familiar with the persistent volume API for Kubernetes, which is like PV, right, like persistent volumes and then persistent volume claims. There's something now similar for what's called devices and then resource claims. There's also what's called a resource slice, and so that's what's going to let you, slice up your GPU as well. Okay, so keep an eye out for those. This API was like heavily like influenced by the persistent volume API, which has been there, pretty early on. One thing I did notice, and this could be a reason why the Nvidia folks are spending so much time now with Kubernetes and getting GPUs to work with Kubernetes, is that right, like the Nvidia folks themselves have this platform called GeForce Now, which is which can stream your games. So say that you're running a pretty low powered PC, or you're running on an old laptop, but you still want to play Fortnite or some of these games. You can actually now use this service by Nvidia called GeForce Now. This is more on the gaming side of their right, like business model. And so they actually have a need to now have like multi-tenant like GPU access coming in from millions of these users that are streaming games. So here's some numbers that they put up, which is 40 plus data centers. They didn't say where or if they're even using any providers, but they do have about 30,000 managed nodes, which they said is about 60,000 managed GPUs. So you get an idea that there's 2 GPUs per node. I believe these are like the RTX type consumer type GPUs, although I'm sure that they're data center GPUs, but more the equivalent. I don't think these are the A100, H100s that we classically talk about in the AI world, the machine learning world. Something that was very interesting is that they do have 1 million plus daily pod churn. So this is pods coming up and then being torn down. So you see some of the volume here, and on the right shows the stack that they're using KubeVirt to create VMs within Kubernetes. They use Prometheus to monitor things. OPA, FluentBit, that kind of stuff. Now, throughout all the talks, they came back to this concept where there's really 2 high-level ways to share GPUs. They're sharing space and they're sharing time. Okay, and space is, really their sort of generic way of saying it's not time-based. So space was a little bit misleading when I first saw them, talking about this, but really it's like, where does the work, or when does the workload get switched in, right? In a time partitions, we're going to essentially run the entire workload on the complete GPU and then time slice it off and run workload 2. And I'll talk more about this here in a bit, but with space, you're actually carving out space on the GPU and then dedicating it to a specific workload. And there's ways to do it where you can do it with software. So the way to split up the GPU using hardware is with something called MIG, which is multi-instance GPU. This is at the hardware level now. NVIDIA lets you pre-configure this GPU to say, I'm going to let you slice up the single GPU into smaller segments. So, and you can define a segments based on memory, based on the actual number of streaming multiprocessors, which is basically cores. But once you configure those at the hardware level, you can't change them. So it has to be done up front and you have to stick to it. So it's not dynamic. These are fixed size partitions, but it does give you full fault isolation. So if you have a tenant running in, this sort of virtual GPU instance 0, that's hardware level, that actually will not affect if there's any errors or faults. It will not affect the tenant that's running in this GPU partition 1, 2, through 6. Sort of interestingly, you can define 7 of these sort of hardware level slices, which was sort of interesting because most things are powers of 2. So I found that kind of interesting, where it's really 0 through 6. So you have 7 partitions that are possible. Okay, so those are hardware partitions. You can run different workloads within those partitions. You can specify those in your Kubernetes YAML. And basically gives you 7 different GPUs that are physically running on a single GPU. Now, there's a software way to do this, which is more dynamic, but it's not really the best. So it's dynamic in the fact that you can create flexible partition sizes, and you can change them on the fly. The problem is you're not isolated at the hardware level. And so if you do have a failure in one of your partitions, one of your tenants is throws an error, this could ultimately kill all of the those other tenants. Okay, so this is logical partitioning, is called MPS, so multi-process service. These take a little bit to get used to. If you look at those links that I'm sure Antje is sharing, you'll see the actual slides that these come from, and then get some more intuition. Okay. And then there's what's called time slicing. I didn't see a whole lot on time slicing during KubeCon. I think this is not really the best way to do it. I do have a comparison chart here later, but for the most part, you want to be doing space partitioning. So I just backed up to the previous slide. And in most cases, I was seeing, well, and there's trade-offs between MIG and MPS, which I'll get to a slide that compares them here in a bit. Time slicing is probably the highest overhead. And not really the most efficient way to do it, but it is giving you the full GPU for a specific tenant, basically, and but it's constantly swapping out and then swapping it back in. Okay, so once again, these are the 3 GPUs. So there was a full talk on benchmarks for which of these strategies. So this was really cool. There were that Kevin Kleus guy and what was the other guy? Yuan Chen from Nvidia broke down for 3 different types of workloads. So for like inference, for a small GPU batch job, and then for large GPU intensive batch jobs, what is the best strategy for this? And to give you some idea here, they were using the Triton Inference Server, which is an Nvidia thing. And they were running, ResNet 50. So we're not seeing the llamas and, things that we're used to. Oh, and then here's the actual GeForce RTX 4090. They define light load as, 1 max thread with a batch size of 1, and a heavy load is 5 threads with a batch size of 5. So this just gives you the sort of context of what these benchmarks that they were running. They also do break down MPS. So again, MPS is the multi-process. This is the software-defined sharing. MIG is the hardware-defined sharing. With the software-defined sharing, there's a way to do it where you specify in your Kubernetes YAML the actual resource limits, or you don't specify the resource limits, which essentially lets a single tenant, without the resource limits, the first tenant that comes in can actually occupy the entire GPU, which is not necessarily the best thing. So sort of overall, and there were about 30, 40 slides that went from this slide to this slide. So this is a gross sort of over summary here, super high level, but really what we see here is, MIG is pretty good. If you're using MPS, you really want to have limits here, especially for these like heavier workloads that have more threads that have higher batch sizes. And, so really you kind of want to stay away maybe from time slicing here. There's usually a better option than using time slicing. That's why I didn't see it much beyond just 1 or 2 talks. And then, so once again, MIG is the hardware level like isolation, and then MPS is the software level isolation. Okay. So These are all in these slides. There's a link here, maybe Antje can share. This is actually a bit of an older blog post, I think from 2022, but all the fundamentals are the same. And compares. So if you're looking for strong isolation, obviously go the hardware level isolation. If you're looking for something with a little bit lower overhead, or more flexibility, because again, with the hardware level, you have to define it up front. How that GPU is going to get split up. And okay, let's talk now. Let's see, for the next 5 minutes, and then I'll wrap it up. We'll talk about fault tolerance. And this is actually, this came up all over KubeCon this year. And I think really it, comes down to, as more and more of these large scale jobs are running, and, as Meta and like Amazon and, right, like OpenAI and folks are training these massive massive models with hundreds of thousands of GPUs. This will be XAI, this will be Anthropic. They're starting to document, where these large scale training jobs fail. And if you're familiar with our Amazon SageMaker HyperPod product or service, this is actually why HyperPod was created, was to help to sort of, I guess, work around or deal with these large scale GPUs. So what was interesting was, in the CPU world, we almost never talk about failed CPUs, right? If you're running a big CPU job, you almost never have CPU failures or memory ECC, right? The error correction errors. These things are just non-existent in the CPU world. In the GPU world, these GPUs are running so hot and designed to just be running at right, like super high heat, and you really have to keep an eye on temperature. And there's so many moving parts with these things, right? And so I'll get into it here in a bit. I'm getting a bit ahead of myself here, but these are highly complex systems with lots of sources of failures. There's power sources, especially when you're doing like these massive jobs and they're all trying to sync the gradients all at the same time. You're going to see huge power spikes. I know the XAI folks had an issue with this when they were building out the Memphis, the famous 100,000 GPU cluster that they recently built with Nvidia. I think it took 19 days for them, which is record time. But they had some power spike issues. When you're working with GPUs, of course, you're moving data between CPUs and GPUs. You've got a lot of different memory banks. You have different levels of cache. You also, of course, with these large jobs, you have network issues, right? And cabling, and then of course, then there's the actual software issues. There's PyTorch issues. There's Nickel NCCL, which is a communication library that the Nvidia folks offer that PyTorch integrates with. There's a lot of places for failure. Okay, and the sort of opposite here is that users expect, and especially from the CPU world, to just fire these jobs off and then not have to think about them. And that's completely not the case in these GPU training jobs. So what can possibly go wrong? Well, as I've been saying, there's quite a lot that can go wrong. And this is actually from this paper from Meta, October 2024. It's called Revisiting Reliability in Large-Scale Machine Learning Research Clusters. So here we see, we have the classic out of memory. That's really the user's fault. But then there's, GPU memory errors. These are sort of hardware level errors. There's NVLink, which is how the GPUs talk to each other. InfiniBand, this is how the nodes talk to each other in these large clusters. There could be like electro, there could be material failures, switch failures. And back to some of the user space stuff, there'll be nickel timeouts. This could be because of a number of different issues. Usually the end user sees a nickel timeout and they start looking into the software layer, but actually it's because of a failed piece of hardware. So you really, when you're debugging these things, have to look at many different places to find the actual errors. Okay. And here's just another one, GPU errors. This is sort of distribution of errors. This is also from a paper. Is it the same paper? No, this is actually a different paper out of Meta, I believe. You have HBM3. This is the GPU memory, all the way down to silent data corruption, thermal issues, all kinds of stuff. Okay. There's these things called disappearing GPUs. There's, let's see, what are some of the other ones that I've seen? InfiniBand, link flapping, bandwidth degradation. Some of the worst failures, by the way, are the ones that slowly degrade. And this is something I remember from my Netflix days, which is the best failures are the ones that fail hard and fail fast. The most difficult ones to debug are when the system just starts to degrade and it's still working, but it's not running at its full potential. Oftentimes at the network level, there's InfiniBand issues, networking issues. The other thing too was faulty fan on a single node that was part of a 400 node cluster that actually slowed down the entire training job. And these are the ones that are really difficult to debug, is when the training job slows down. And let's see, one of the speakers said something interesting that really stuck with me, which is in this sort of high performance computing, we'll just sort of generalize all of this as HPC, high performance computing. In the high performance computing world, you go into your cluster right when you start the job or before training, before running the training job. You assume that all the nodes are broken and you want to prove that they're all up and running before you start the job. And so, once again, very different than the CPU world where you assume everything's working and then you only deal with the failures. And so there's this real sort of emphasis on pre-flight checks. You want to check all the nodes. When I work with customers, we run a lot of nickel tests to make sure, basically simulating what the training job is, going to do at the lowest levels. Check to make sure that the links are all set up properly, and that there's access to the model, to the checkpoints in the storage system. Check all the GPUs. Check the temperature. Check the memory status. Check that all the nodes are healthy, check that all the links between the GPUs and between the nodes are all working properly. To do this, you have to have really good monitoring. You want to propagate these errors that you see, these metrics that you're paying attention to, heartbeats. You want to look at error codes. You want to look at the model flop utilization, which is what a lot of folks look at, which is how sort of what is my aggregate, GPU utilization throughout the entire cluster. You want to then be able to recover, so you have to propagate these errors. You want to be able to take nodes out of your system, put like what's called I think it's cordon, CORDON, pull them out of the cluster. You want to then be able to recover from these failures pretty quickly. And, I'll say at scale, I see about 2 to 3% almost of the GPUs tend to fail and always be in a failed state. And this is exactly why the SageMaker HyperPod service was created, was we actually have a pool of about 2 to 3% of the total GPUs in the system waiting and offline. They're warmed up and ready to be swapped in when the GPUs in your main training cluster have failed. And so we can very quickly recover. And what you want to be able to, reboot these nodes or to pull them out of the cluster and then put in the sort of warm pooled one that's waiting. This is a very, very interesting paradigm. One that might not be familiar to a lot of folks without doing some of these large training jobs. One thing to highlight is DCGM. I can never remember what it stands for off the top of my head, but you want to be exporting these into your, either Prometheus, or if you're using like AWS, you want to be exporting them into CloudWatch and keeping an eye on these metrics. So, these are going to be your error counts, the GPU utilization percentage, temperature, fan speed, and be, keeping a very close eye on these things. You also want to be checking your kernel logs. You'll see XID. That's going to be, the actual error ID that's coming out, GPU driver errors. So there's a whole lot that goes into this. RDMA, which lets one GPU talk to another GPU directly without having to go through the CPU memory, without having to go, through multiple hops. So, once again, a lot of moving parts here. So I mentioned this, there's ways to actually remediate, when something fails. The second one here I've mentioned twice, which is using Amazon SageMaker HyperPod, where you have a warm set of spares. This is all done for you. You do not pay for those warm pool nodes that are waiting out there, and you don't have access to them until something fails. Then HyperPod kicks in and then replaces those failed nodes. The other way, which is actually a little bit slicker, is that you can rely on software to, and this is now supported by PyTorch, but fairly recently, I think with PyTorch 2.4, or yeah, maybe even like the latest 2.5, there's something called flexible checkpointing, where and so like, to be very clear, because there are so many GPU failures, you have to be checkpointing very frequently. And so PyTorch actually has a newer way to do checkpointing, where it can do it in the background asynchronously, where it's not going to halt the entire training job, which is how the old way of checkpointing would halt the entire training job. All 10,000 nodes would write the checkpoint out to S3, and then training would continue. If you're not checkpointing, which is just crazy to think about, you would essentially have to restart the training job from the very beginning. So you want to be using checkpointing. But there's now what's called dynamic checkpointing, which lets you run a cluster of, let's say, 10,000 nodes. And if there's a failure, you can restart the training job with 1 or 2 less nodes and train with 9,999 nodes. And PyTorch will actually be able to read the checkpoint that was written by 10,000 nodes and change it down to 9,999 nodes. Now, this does put you in this what's called reduced world like scenario, but it does give you time to then debug and figure out what was wrong with that node. And that's a way to do it if you're not using something like HyperPod. And at the time HyperPod was created, PyTorch did not support this dynamic checkpointing. And so, but there's now more options to use. Okay, so here's the references. I'm sure Antje put these in the links or in the chat here. Antje, are there any questions that I should take, or should we wrap it up? For about 20 minutes.
I think we can wrap it up. I don't see any questions. I think this was an amazing summary of the GPU highlights. Folks jumped in here and looked up DCGM, stands for Nvidia Data Center GPU Manager. Thanks for looking that up.
Yeah, DC's data center. Okay, gotcha.
Yeah, there's one question coming in. Is MIG supported on all the GPUs?
No, MIG is, I don't know the cutoff, but MIG is only newer GPUs. Right. Good question. And also, I should mention, there's ways to combine. I think I had it in the bullet point here, but you can actually combine these strategies. So I didn't want to get into it here because there's way too many like combinations, but like you can actually combine time slicing with the space, like partitioning, and do all kinds of like different tricks here. But once you start doing, and they showed the YAML for all of those different variations. If you look at those links that are referenced here, they show all the different combinations and ways to do it. But yeah, awesome. Thanks, everyone. I'll post this video later today and share it on the Meetup and share it on social. Thanks for coming.
Thanks, everyone.